Cool. All right. And we'll just wait a couple minutes for folks to log in. Oh, and the Zoom call automatically starts recording. I forgot to mention that as well whenever we go live. So it's already started recording at this point.
Got a lot of people checking in.
Yeah, fantastic. Cool. Well, we'll wait another minute or two, I guess, just to make sure that we've got everyone on. All right. So I think we should get started. It looks like we've got a good crowd. So welcome everyone. Good morning. Thanks for joining us today. We have a great talk lined up by Dr. Evangelos Farantatos, who is Senior Project Manager at Grid Operations and Planning R&D Group at EPRI, Electric Power Research Institute. And he'll be talking to us today about how we can move towards electric power systems dominated by inverter-based resources. Dr. Farantatos received the Diploma in Electrical and Computer Engineering from the National Technical University of Athens, Greece, and then his master's and PhD degrees from the Georgia Institute of Technology in Atlanta. And as I mentioned, he's now with EPRI at Palo Alto in California. So really appreciate you joining us this early. I know it's a little after 7 a.m. So thank you for the early start. And he manages and leads a number of different projects related to synchrophasor technology, power systems, monitoring control, power system stability and dynamics, energy sources modeling, grid operation, and several other topics related to inverter-based resources. He's a senior member of the IEEE. And I know that many folks will find this talk interesting because, of course, it's relevant to a lot of the work that we do here at NC State and in Freedom and elsewhere in power systems and power electronics. So I think that's well reflected by the large group of folks that we have in attendance today. Just a quick reminder, logistically, we've got the Q&A function enabled here in Zoom. So if you have any questions, please feel free to post them within the Q&A. We'll keep an eye on it. And Vangeli, a quick question for you. Do you want us to pass on the questions to you as you go, or should we collect them and ask you questions at the very end? What would you prefer?
Yeah, you can stop me and ask question, especially if the question is related to a specific slide or something that I said before. If it's more generic, I would prefer to answer it at the end. Maybe it will be answered during the slide. So
okay.
Is that okay?
Yeah, absolutely. That's totally fine. So I'll keep an eye on it because I know with screen sharing it can be hard to see all those things happening. And if something pops up that's relevant right there and then, I'll let you know. Great. Yeah. Well, with that, welcome once again, and we look forward to the talk. It's all yours.
Thank you. Thanks, Spiro, and thanks again for the invite. I'm glad to give this presentation here to the group for the NC State University. As Spiro said, the topic I will be presenting on is a little bit high level towards electric power systems dominated by inverter-based resources. But I believe it's reflecting what's going on now in the industry. There are huge transformations happening now in the power systems industry. A great time to be a power systems engineer, and especially in the R&D. So what I have is a bunch of slides that cover different topics and try to address the multifaceted challenges that are created by by increasing number of inverter-based resources that are introduced in the system, and how the generation mix is changing, and how it is affecting the system, and especially the reliability of the system. So before going into the details, I have a slide for EPRI, for those that are not familiar with EPRI, the Electric Power Research Institute. So our mission is to advance safe, reliable, affordable, and environmentally friendly, responsible electricity for society through global collaboration, thought leadership, and science and technology innovation. EPRI is an independent organization, and we are also a non-profit organization. So just to clarify, we are not affiliated with government. And our business model is collaborative, so we work with scientists, engineers, universities, academia, vendors, and consultants and other industry experts, again, with the ultimate goal as our mission is to advance electricity. A few more things, specifically for the group I belong to. It's transmission operations and planning. It's actually grid operations and planning, which has two pieces, the transmission operations and distribution operations and planning. But as I will say, there's a lot of synergy between those two. So there is, we work a lot across different groups and across different programs within EPRI. So the different aspects that we are working on in our group, it's a group of about 50 plus people, I would say. Now it covers topics from the long-term planning of a power system, resource adequacy, analysis that is done for 10 plus years, looking into the future, transmission planning, several years ahead or 1 year ahead, or things like that, and then moving into real-time operations planning, down to the control center operations. On the same time, a lot of work on market operations, which covers different time scales, and also protection, which covers, again, both planning and real time. So the slides I have next, I'll try to follow also this kind of diagram here and this kind of time scale. I'll try to address the challenges that we have for different pieces of those different kind of studies and different areas that we are doing, and the R&D needs for the future grid that, again, is dominated by inverter-based resources. So let's start. Basically, what is the motivation here? As I said, there are huge transformations that are happening now in the power system. In a conventional power system, we have the transmission, the generation, which is based on fuel-based conventional synchronous machines that are generating the electricity. This is stepped up to high voltage in order to transmit the power down to the distribution system, where the customers are connected, which can be residential loads or industrial customers. So two major things that are happening. The synchronous generators that are traditionally, again, providing the electricity are being displaced by inverter-based resources. We refer to them as IBR, which is primarily wind, solar, PV, but also storage. Let me see if I can get my pointer. So one thing is that the generators are displayed. So we have now a different generation mix with more and more renewables connected in the system. But the other major difference is the connection point. So now we have generation also down at the distribution system, very close to the customer. Some of them, for some of that generation, we refer to as behind the meter. So a solar panel that you can install in your house is referred to as behind the meter. This is again something totally different. We have a generation very close to the customer down at the distribution level, and that changes basically everything with regards to planning and operation of the system. So what drives this increasing number of renewable connections is basically targets by governments and others with regards to carbon reduction and clean energy transition of different countries. And there is a lot of analysis that is being done, different carbon reduction models and scenarios, 100% renewable scenarios, carbon-free scenarios, net zero scenarios, and for each of these scenarios, there are different forecasts in terms of the capacity of renewable generation that is expected to be connected in the system. And you see that it's several hundreds to more than 1,000 gigawatts of additional or of solar, wind, and also storage that is expected to be installed in the system in different countries, not only the U.S. This is for the U.S., but in general in the power system. And also there are what we call renewable portfolio standards that are set by different states in the U.S., but also from different companies, utility companies, and some of them are very aggressive. For example, you can see in Hawaii there's 100% RPS, renewable portfolio standard, by 2045, and others are following, and these are updated, annually, depending on the progress. So we recently published a white paper at EPRI. In my slides, I have a few links of public reports that you can refer to and you can download. This one is a very, very recent one. It's called Powering Decarbonization Strategies for Net Zero CO2 Emissions. So I definitely suggest that you download and read that. It describes different carbon reduction models in the future and the expected additional capacity of renewables that is expected to be installed for each of those scenarios, and provide some recommendations on strategic recommendations on how the power system will be look into the future. So to support all this transition to an energy clean power system and with inverter-based resources dominating the system, there are different types of studies that we have to do and we are doing. So from a more strategic level, there is a lot of national and state level policies analysis that has to be done. Individual companies, they set their own strategies, as I said, to meet either their individual goals, but also to comply with the state renewable portfolio standards. And then studies and models with regards to renewable integration, energy storage, projections in terms of the expected capacity, energy sufficiency. And then there's a lot of also discussion and activities on electrification also. So electrification of transportation, electrification of heating, and how is this going to affect the electric sector in the future. Again, strategic planning and analysis that is needed for this. Now, on top of that, and something that is more related to what I do and what we do in our group, is analysis related to the reliability and resiliency of the grid. So we develop different methods and tools to perform this analysis and different models to support the analysis and all the simulation and the case studies that we are doing with regards to reliability and resiliency, with regards to system restoration, if you have a blackout, model development and validation, as I mentioned, resource adequacy assessments, protection and planning, etc. So a wide variety of different tools, methods, models, and analysis that we are doing, and we are conducting R&D to see how these tools and methods and models have to evolve in order to support the changing grid and the transforming grid with the increasing number of inverter-based resources. So, as I said, all these changes are driven by the installation and integration of the inverter-based resources. So, what are the characteristics of those that are creating those challenges? So, these are the three ones. The first one is the variability and uncertainty of those resources. The second one is the fact that they are inverter-based. And then the third one is that their location, as I mentioned earlier. So with regards to the first one, especially for wind and solar resources, as I'm sure you know, the energy generation depends on the wind speed or solar irradiation accordingly. So there is a lot of variability and uncertainty within that. So the output varies across seconds, minutes, and we have tools that to do forecasting, but it's forecasting as you get higher and higher levels of inverter-based or variable resources in the system becomes more challenging, and that's an evolving need to develop more accurate forecasting tools to forecast the variability and the uncertainty of these resources. The other major difference is, as I said, they are inverter-based. So a conventional synchronous machine that is providing electricity in a conventional grid, it's a huge mass of a generator with all the electrical, its impedance, electrical characteristics, its impedance and resistances and everything. Inverters are connected to, or renewables are connected to the grid through inverters. So, so the way they behave depends highly on how you control it. So it depends highly on software, comparing to generators that their output is dictated by physical loads. So as these resources are displacing the traditional machines, then we have to rethink how we control the grid. How do we program them? And how we have the power electronics to behave for the inverter-based resources to provide the performance and the services that we need for the grid. And then the last one is, as I mentioned, the location. So now we have generation down at the distribution level, which means that we might even have backflows of power back to the transmission system. So what we have now bidirectional flows of power We have load that is covered by the generation close to it. So, but on the same time, all these resources, as I said, they are inverter-based, so they can provide also services both at the distribution but also at the transmission level. So again, that's a huge difference. So let's start with, as I said, with a few different topics, and I'll try to address the challenges and what we are doing to address those challenges. So the first one is resource adequacy. What is resource adequacy is an assessment whether the current or the projected resource mix is sufficient to meet the capacity and the energy needs. So as I said, with the increasing integration of wind, solar, batteries, and other resources, both at the transmission but also the distribution system, there is a huge need for new resource adequacy models, new simulation tools, standards, customer behavior analysis, but also a lot of probabilistic and a lot of stochastic analysis and methods that have to be introduced and developed to address the uncertainty and variability that these new resources are introducing in the system. So again, the main point here is that the traditional tools that we have been using to perform this analysis of resource adequacy, we see more and more, and as we are investigating scenarios with very high levels of renewables, we see that these tools, these traditional tools, are not sufficient, and we have to go to develop new tools, new models that are becoming more complex because we have to introduce stochastic models. We have to use probabilistic methods in order to address the variability of these resources. And we start seeing issues with resource adequacy. You might know of the California event back in August. Not event, but yeah, kind of load shedding. So what happened? There was a heat wave for a few days across California, and the California ISO, the system operator, they had to do what we call rolling outages. So they had to load shed specific pockets in the system because the generation was not sufficient to cover the load. There are many factors that contributed to that. The main reason was the heat wave, but there was some loss of other generation units on that day. There was not sufficient imports from neighbors. There were some outages. So that was a trigger, we after that event, we published a report that basically identifies the challenges of the resource adequacy, and especially with regards to what happened in California. So this is a public report. I have the link in the slides. I'll send you the slides. Again, I encourage you to download. And if you are not familiar with the California event in August, I'm sure you are familiar with what happened in Texas, which is kind of similar, but what happened was to a greater extent. So instead of heat wave with Texas, we had the cold. So basically, the resources, different types of resources, they could not meet the expected performance. So you see that there is natural gas, there's coal, there's nuclear, there's wind, and there's solar, and all of those generation types, they basically performed or could provide generation below their capacity due to freezing pipes and due to lack of natural gas, for example, for the natural gas generators, and other issues. This is an ongoing analysis that we are doing in collaboration with our EPRI members, and especially ERCOT. It's a very recent event, but main point here is that some try to blame the renewables for this, but as you can see, the analysis shows that the renewables were not the reason for this happening. Actually, the renewables, they had similar performance with other generator types, natural gas or coal or nuclear, and also the expected capacity for wind and solar those specific days was a small percentage of what was supposed to be provided by the other resources. So you see that ERCOT had kind of expected that.
Vangeli, there was a question.
Yes.
Sorry to interrupt. There was a question that came in on the previous slide about why would nuclear reduce during that time?
Again, it had to do. I don't know the details, but it has to do again with delivery issues of the energy. It might be again pipes or other things that, due to the coal, prevented the generation from those units. Yeah, unfortunately, I don't know details, and it's also something that it's an ongoing, analysis that we are doing and going into the specifics. Yeah. But you see that nuclear, with regards to the others, the performance was higher, approximately 80% compared to the approximately 55% of the other resource types. So it was less effective, I would say. Yeah. And basically, before the event in Texas a few weeks back, it was at EPRI, we had published a technical update in late 2020 that was talking about that specific thing: impact of extreme events, natural gas, fuel, and other contingencies on resource adequacy. So it was describing the main challenges that extreme events are introducing, and resource adequacy problems that might occur from extreme events like freezing weather, wildfires, droughts, or heat waves like what happened in California. So this was a report that was only available to the EPRI members, but after what happened in ERCOT or in Texas, we made that public because it was exactly addressing what happened. So that's another document that I encourage you to download and read. So moving from resource adequacy to planning and modeling. So basically, the motivation here is that as these resources are being integrated in the system, we start seeing some kind of reliability issues. So these are a few disturbance reports that were published by NERC the last few years. They described in detail some events that were related to mostly photovoltaic resources, and basically all these disturbances, they motivated a lot of work that we started a few years back on the need for accurate modeling of inverter-based resources. So in order to perform the reliability studies that we do, and these are typically power flow studies as we call them, or kind of dynamic stability studies, or transient studies, We do them to, inform transmission or system planners, transmission and distribution planners, inform them and with regards to reliability decisions that they have to make. So in order to perform accurate studies, we need accurate models. So this is how an inverter-based resource plant looks like. So we have the inverter level. We have typically a voltage source converter that is connected to the system, and then you have all the different controls at the inverter level, outer controls, inner controls that are generating the switching signals for the power at the power electronics to basically to generate the electricity, and then we have also plant control levels that basically are providing reference signals to the individual inverters. So if you have multiple inverters in your system, you have also the plant level control. So I'm showing the slide not to go into the details how the different inverter blocks are, but to show what I mentioned before, that this is not a synchronous. This is totally different from a synchronous machine. Again, the synchronous machine is a big mass of equipment with a rotating mass with all these physical, electrical characteristics with its impedances, resistances, reactances, etc. This is all power electronics and software. So the inverters, they behave depending on how we program them and what we ask them to do. Of course, there are limitations, physical limitations in terms of the limits of the power electronic switches. They have thermal limits. We cannot exceed specific, currents, not to burn them out. But this is part of the design, right? If you design them appropriately, they can perform depending on how, and they can do whatever you ask them to do. The other challenges that we see with regards to modeling is that we need to perform now more detail. We see the need to perform more detailed analysis and use different tools and different models to do our studies. So traditionally, what we have been using is what we call RMS models. These are models that are modeling the machine electromechanical dynamics, and then for the electrical, electrical quantities like voltages and phasors, we represent them all in steady-state phasor domain. So there are traditionally we were doing in generator like dominated systems or in conventional systems. There are some simplifications that we were doing in the models when we are doing the stability analysis and the dynamic analysis, because the dynamics of the synchronous machines are electromechanical, and we could do some simplifications in terms of the modeling and the studies we were doing are accurate. But now with these new devices that are again power electronics based, we have to go into more detail into the modeling. So we see the need for more what we call EMT modeling, electromagnetic transient modeling, which means that all the network devices and controls, everything is represented with detailed models with differential equations and things like that. We've seen cases. This is an example from the Australian system operator. We see cases that the traditional RMS models are not representing what actually might happen in the system. So here you see a simulation shows that or the RMS simulation shows that the system is stable upon an event, but actually when we do the detailed analysis with the EMT model and detailed representation of the controls in the inverters, the system is unstable. So again, bottom line is that if we continue to use these RMS models, then we will not be able to capture accurately through the studies the reliability of the system. So what is the need here? The need is, there's a lot of discussion on transitioning to more EMT models and simulation. However, the challenge here is that this requires a new expertise for power systems for all of us. It's not as straightforward and easy to develop an EMT model and do simulations. And also the other thing is that these simulations have a very small time step, so it might take hours, to run a 20-second simulation. So there's a lot of research needs here in terms of modeling and in terms of tools that will be able to, to use to perform accurate studies. The other challenge is availability of the models. So going back to the, again, referring back to the generators, building a model for a generator is pretty straightforward. Again, if you have details and information on the physical characteristics, the impedances and the resistances and things like that of the generator, you can easily build a model. And we have been working on that for decades, and this is quite mature. The challenge with the inverters, as I said, is that everything depends on how you control them, what goes into the software of that specific inverter. We have what we call user-written models that basically are provided by the inverter manufacturers, or that they know what they put into the software into the inverters. And we have also the generic models that we try to mimic the or try to capture the dynamic behavior of those inverter-based resources. But the challenge here is that there's no standardization and there's no specific requirements on how these inverter-based resources should behave when they are connected into the system. So that makes challenging the development of the generic model. And where do we use the models? We use the models to do interconnection studies. So starting from initially a feasibility study that the utility or the transmission owner or the system operator will do to see if there's a specific interconnection request. The objective of this feasibility study is can that be integrated to the system? And then there's a system impact study to see how for different events and how for different contingencies the entire system will behave with these new resources. So at this stage, for these studies, we need generic models. At this stage, the transmission planner does not know the specific model of the inverter, does not know the vendor. So again, given that how the inverter performs depends on how it is controlled. If you don't know what's if you don't know the the control settings, you cannot perform an accurate study. So there is a need for standardization in terms of the performance of those inverter-based resources. And this is where this new IEEE P2800 standard is coming into the game to address this challenge. So basically, this is a new standard that we are working now and drafting, and EPRI is heavily involved in this activity. So this is a standard to harmonize the interconnection requirements for large solar, wind, and storage plants. This is something that we started back in 2019, and the first draft was recently approved late last year, and now we are going through the balloting process, and we expect to have the standard published by the end of the year. So what this standard is doing, it's describing technical minimum capability requirements and performance requirements for these inverter-based resources. So, without going into details, it discusses how these resources, what should be their frequency response, what should be their reactive power and voltage control capabilities, right through, but also it covers modeling, model validation, and testing. I want to emphasize that this standard doesn't address or doesn't discuss anything about utilization of these capabilities. So utilization of these capabilities is up to the utility that basically performs the interconnection studies and sets the interconnection rules for them specifically. So to give a specific example, the standard, for example, says that during a fault you should inject, you should have the capability to inject reactive positive sequence reactive current and negative sequence reactive current. It will not tell you how much and for how long and what are the specifics, but again, it discusses or it requires the capability of doing that. And the other thing I forgot to mention is that this standard, the 2800 standard, focuses on transmission level connected resources. So inverter-based resources connected at the sub-transmission and transmission level. Then we have the, as I mentioned, the other major transformation is happening with the connection of those resources at the distribution level, and we refer to those as DER. So in terms of the interconnection requirements, we need performance capabilities and performance requirements for those resources as well. So for that, similar to the IEEE P2800 standard, there is another standard for DERs, for distribution connected now resources, 1547, which was drafted in 2018. So basically the 2800 came after the 1547, and people are now starting adopting the 1547 for distribution system. But that's not the end. There's a lot of research and development and standardization needed with regards to utilization of these resources now and how they can provide services into the system. So basically, how you control, how you manage, how you control these resources either individually or through aggregators. And recently, there was a FERC order 2222 that basically allows these DRs to participate into the market in different energy products, capacity products, or ancillary services. So again, we see that, we expect and we see now that the DRs are having a more active role into the overall power system, and so this is a huge transformation that's happening now in the power systems industry. And yeah, this is a slide for the IEEE for 1547 that I mentioned before. So this was published in 2018. And again, similar to what 2800 targets to do is describes capability and performance requirements. For example, voltage right-through requirements for DRs, but also frequency right-through requirements for DRs. So if this slide is trying to put all these things together, so basically modeling, interconnection standards, and modeling and model validation and testing. So basically, again, starting from the performance requirements, we have now standards, the 2800 that is, we expect to have it by the end of the year, 1547. Those, I want to mention that these IEEE standards, they are voluntary, but then the utility interconnection rules can adapt them and mandate them. So that's the value of those. Then we have testing and verification for the inverters in order to make sure that they comply and satisfy the performance requirements set by the different standards or the interconnection rules. And then we have model development, as I mentioned, and then model validation or performance validation based on actual field measurement. So this is like a circle that goes and goes and will go for the next years as things are evolving. To address this, all the challenges related to modeling, I wanted to quickly mention a project that we recently got awarded by DOE, Department of Energy, the Solar Energy Technologies Office, CETO, that is trying to address exactly this challenge, the need for publicly available generic models that can be used in different types of studies, protection studies, stability studies, steady-state power flow studies, in order to support the transmission planners and distribution planners to perform interconnection studies and also security assessment studies of inverter-based resources. Now, another hot topic now in the industry is the need for what we refer to as advanced inverter controls. So again, in a synchronous dominated system, basically how the IBR behaves is that there's a change in the system. The inverter is following that, and depending on how it is programmed, it's injecting some amount of active and reactive power into the system. And this is, recently has been labeled as a grid-following inverter. So basically, an inverter that is, depending on how the system is behaving, that it behaves accordingly. As we go into the IBR dominated systems, we see challenges with regards to these grid-following inverters and the need for more advanced controls that are referred to as grid-forming. So grid-forming is basically, before going to definition, just showing some different inverter controls that have been proposed in the literature for grid-forming inverters, like a virtual synchronous machine or troop-based control, or the virtual oscillator control. But this is not an exhaustive list, and again, this is a topic that there is a lot of research going on now. But yeah, and from our side, if you ask what is a grid-forming inverter, what we propose is that the definition should not depend on the control design. The definition a grid-forming inverter should be defined based on its capability and grid services that it provides. So if it can operate in a system with 100% inverter resources, if it has the control capability to do that, this is what is referred to as a grid-forming inverter. I see we're kind of running out of time, so I'll try to go quickly through the next slides. We talked about planning and modeling. The next topic is operations, and this is kind of a slide that summarizes the state of the art in grid monitoring and control. We have SCADA, we have energy management system, which is a centralized grid monitoring and control architecture. In terms of the monitoring, there is a lot of advancements. Last few years, we have what we call now phasor measurement units, that they provide high resolution measurements, and also measurements that are synchronized on a common time reference So these units, these measurement units have a DPS that timestamp and time align these measurements. So basically, again, this is a comparison between synchrophasors and SCADA. You see the high resolution that allows us now to see better, monitor better, but also control the dynamics in the system. So the main question here is, as we move toward systems with high levels of inverter-based resources, how do we control the grid? Because traditionally the synchronous machines are the ones that are providing frequency and voltage and other kind of control services in the grid. So specifically for frequency control, the question is, can wind and solar provide frequency response? And the answer is yes, if there is available headroom. So if they don't operate at the maximum power tracking and there is some headroom, they can provide some frequency response. They can provide fast frequency response and also participate in the ADC, which is the automatic generation controller that is used for frequency control. But going beyond that, we see that if we ask the inverters to behave like they do like machines behave in traditional frequency control, that's not efficient. So we see the need for moving into hierarchical decentralized control schemes that take advantage of the inverter capabilities to provide fast controls. So we have a white paper also published that summarizes our vision here on decentralized hierarchical controls that I encourage you to read. I'll skip those. The last one, just quickly, that I wanted to touch upon is protection. That's another area that we see a lot of challenges. Again, the motivation here is that the inverter-based resources, the fault response is totally different compared to synchronous machines. So the fault current that they provide is very small compared to what a traditional generator is providing. So the design we have to rethink and redesign the protection system. So we've done a lot of analysis with our EPRI members, but also with collaboration with EPRI. We have developed new models for inverters to perform short circuit studies, and we have done a comprehensive performance evaluation of different protection schemes that are now being used and how they can be affected in the future by high levels of inverter-based resources. And we provide recommendations in terms of different how to adjust the settings in the relays or how to design new protection schemes to address those challenges. Yeah, and so that was the last slide, and this is the last slide. Basically, bottom line here is that there's a lot of work that is going on, and at EPRI we are leading a lot of R&D research on these areas. Hopefully, I got the message to you that there's a lot of activities in the areas of power systems now. So if you are interested, there are and you would like to join EPRI, there are several open positions now. So again, it's an exciting time to be a power systems engineer. So with that, I'll pass it back to you for questions. I think we have 5 minutes.
Yeah, absolutely. Thank you very much, Vangeli. That was great. You covered a lot of really interesting topics, and I really appreciated that you made it clear how this is relevant with like real world events as well, fresh on our minds. So we actually have some good questions that came in, so I'll go through these. One of the ones that came in was, is the interconnection standard designed for the IBRs, or is it the same for all generation sources? For example, the same standard applies to conventional generators.
So these the standards that I mentioned before, the 2800 and the 1547, these apply for inverter-based resources. And again, the reason is that the performance of those resources depends on how you control them. What software do you put in the inverter controls in the power electronics. So there is no standardization on that. So the vendors basically they can have default settings, but the default settings we don't know if that is sufficient for the grid. With conventional generators, we know how they behave. We have been studying them for decades. And again, their behavior depends on physical laws, right? On their impedances or on their physical and electrical characteristics. So it's a lot easier to model them and assess their performance. While for the inverter-based resources, we need standardization. So yeah, to answer the question, these standards they are only for inverter-based resources.
And a similar question related to that, someone points out there are a lot of inverters already connected to the grid. So how will these existing inverters be brought under the new standards?
Yeah, that's a good question. So so basically, since the response is based on the controls, this is something that can be easily updated or retrofitted, right? So if we see that existing resources based on the controls they have now, they don't meet the performance requirements, it is up to the interconnecting utility and also the vendor to work together to update the controls in order to meet the performance requirements.
Got it. Thank you. And the last one that I have here in the list is how does one distinguish if the instability behavior in EMT simulation comes from EMT behavior or due to bad modeling in EMT, especially because most existing standard dynamic models, for example, Exciter, Governor, PSS, etc., are RMS models? Yeah,
that's also another good question. So when you run a simulation, you have to be confident on the model, right? So if you see that the system is unstable or whatever, it might be from bad modeling, but it also be due to that's how it should behave. So that specific reasons that specific reason I think or the question is kind of enforcing the need for accurate models, and that's what, as I mentioned, that's what we have been working a lot, especially the last few years. So make sure that we have accurate, detailed, and models that we trust, models that we have validated against actual events, validated based on in collaboration with the vendors. So we need to make sure that we trust the models. So if we trust the models, then we trust also the simulation results.
Fantastic. So we got a couple more questions if you still have time. One question came in, a very pertinent question is, what are some opportunities for collaboration with academia, and in particular, I guess, with NC State? I know we have a lot of power systems research going on here as well. How to best interface?
So actually, we work at EPRI. We work a lot with universities, and I have personally also worked, or I'm working with NC State, and we have actively now students actually that are doing internship from NC State in my team, and I have worked with some of the professors. So. Collaboration, it can be through proposals to DOE or other funding agencies that EPRI can partner with NC State and submit proposals, or it could be through a direct, like a contract or agreement between EPRI and NC State, with NC State being a contractor and perform studies and R&D projects. So there are multiple ways of collaboration that that can happen and are happening. Yeah.
Thank you. And we'll do one last one here. Another technical question. Can you please comment on how to solve grounding issues for the IBR devices and protection?
Yeah, that's a question. Yeah, I don't think we can answer that in a few minutes, but there's a lot of work that is done with regards to grounding and inverters and how that affects the protection. Yeah, it's another challenge that we have several projects that are addressing that. Yeah.
Awesome. Maybe it's in one of the reports that you pointed to as well.
Yeah.
Fantastic. Cool. Well, thank you. That was, I think we got through all the questions, and it was really great to hear the perspectives here. I'm glad to hear that you have ongoing collaborations with NC State and students and so on. That's really encouraging. So I want to do a virtual applause one more time for Dr. Farantatos. Again, thank you for the presentation. And we'll send out some information about the slides that you gave and that you presented, and the links to the reports that you mentioned as well. And just for the audience, I also want to mention that we do have another colloquium scheduled for next Friday, and it will actually also be in the theme of power systems. We have a speaker who will be talking about developing grids and other power systems within rural Africa as well. So kind of related, but also different scenario, different environment. Cool. Well, thank you everyone for joining us today. And once again, a big thank you to our speaker, Dr. Farantatos.
Thank you again for the invitation, and yeah, hopefully it was informative.
Absolutely. We enjoyed it very much.
Thank you.